Hello all, this is Muhammad Hanif from RGOKT Basar. Once again, welcomes you to this lab session on subject digital signal processing. So in last three sessions, we have seen that how we can work on simple generation of sine wave, and then we have successfully able to generate the musical tone, and then we have worked on a linear convolution. Now, today we will be seeing that how we can do a simple filter, a simple low pass filter. We'll start with. Okay. So for that one, once again starting with CLC, clear all, close all, and then first, as usual, we need to define a sampling frequency. Okay, sampling frequency, and then TS is equals to 1 upon Fs. Okay, and then NTS is equals to 0 colon TS to 1. Okay, so basic idea here is to do filter. So we'll be taking two signals as x1 and x2, and then we'll convolute with one impulse response of low pass filter first. And here we must know the filter coefficients of low pass filter, and then we can use those elements, and then we can use those elements to do the convolution with our input signals. Okay, so here first we try to generate two different signals. So let's say f1. So here input enter first frequency. Okay, and then second. So we'll copy this here and paste it and change the name as f2, and then say is that it is as second frequency. Okay, and now so we have to know the filter coefficients of low pass filter. So for that one, so we know that h of z is given as 1 plus z upon minus 1, and then so here it will be 2. So this is a filter in Z transform. So if you calculate this, and then we are going to get uh, capital H absolute value of capital H e power j omega as cos of omega by 2. Okay. So from this, if you solve this one, we are going to get a plus half and plus half. Two halves will be available in filter coefficient. So we are going to use those things in our Matlab program. So defining those as h is equals to 1 by 2 and 1 by 2. Okay. Now defining the first sequence, so the first signal, so cos 2 into pi into f into t. So or instead of t, actually it is nts, right? This is the first signal generation, and copying the same and pasting here and changing it with to x2, and this time so here we have to write f1 and this will be our f2. Okay, so now we are able to successfully generate the two signals. Next, we have to do the convolution. So for that one, we take y1 as y and b, the convolution between h and x1, and y2 is equals to convolution between h and x2. Now, after convolution with these filter coefficients, as these filter coefficients defining the low pass filter, we can see that below the cutoff frequency, the if the frequency is like near the cutoff frequency or under the low pass frequency band, then the signal amplitude will be remain same, or else it will be reduced. So here the amplitude is a. Normally we have not defined the a, so we'll take that as a 1. So here also we have defined as a 1. So in the output after filter, we can see that these frequency amplitudes will be reduced. So whichever frequency is uh, having higher value, that will be having a less amplitude compared to the uh, signal which is having a low frequency. So here we'll try to define f1 as a low frequency and f2 as higher frequency, and then we easily compare it with. Okay, so first we'll define taking us one sequence or already as is mentioned here. So we'll try to plot. So I'm plotting the first signal only. So plot, let us go with NTS comma X1. Okay, so we'll plot this first. So we are running the program. So sampling frequency, let's go with 4000, and as its sampling frequency is 4000, we are restricted to use the input frequencies not more than 2000. So first I am taking as 500, another is as 1000. So this will be our 500 signal frequency. Okay, so you will be having a 500 sine waves here, and you can see that the amplitude is 1. Okay, so as we are not interested in this complete frequency band, we are interested only in amplitude, so we can reduce the sequence here. So what we can do is, so we'll define n1 as 0 ts, and we'll define only 5 cycles in the f1. So we say 5 divided by f1. Okay, so we're going to get only 5 cycles, and then taking the length. So let's say L1 is equals to length of this N1. Okay, and copying the same thing and pasting here, and then mentioning is that N2. So this will be, again we are interested to have only 5 cycles, so this will be N2, and then this will be L2. Okay, now saying figure 1. So figure 1, so we'll try to draw plots, one plot for x1, another plot for x2, and then y1 plot, and then y2 plot. Okay, so already we have seen that how we can divide a, this plot window into subplots. So using that subplot, so as we do need 4 plots, so say 4 rows, 1 column, and the first one, so let's say it is plot. So instead of NTS, we'll write N1. Okay, N1, and then this one will be x1, and so if you draw the x1, so here the length will not be matched, so we have to reduce the length also here. So how we can do that? So x of, and then say up to length of L1. Okay, so and plot this is okay, and say we'll give the x label for this. X label will be time in seconds, and then y label will be amplitude, and then title will be the first signal x1, right? And we'll copy this from up to here, and now we'll paste it and say subplot, this is 2, and instead of n1 is okay, instead of x1 we'll say y1, and say this will be filtered output for first signal x1. Okay, or you can say input output or first, that's it. And once again we paste it, and this time we'll change it to 3 and say instead of n1 we'll take n2. Okay, so this will be n2, and this will be x2, and this will be l2, and this will be our title will be second signal, right? Second signal, and this will be x2. Okay, so we'll copy this one and paste it, and then we'll say the subplot to 4, and this will be instead of x2 it will be y2, and remaining same remains same, and this will be filtered output for second signal x2, right? So we'll run this, enter the first frequency, sampling frequency, so as it is 4000 and 500 and 1000. So if after running this program we must see that the 500 signal amplitude will be greater than the 1000. Okay, so here you can see that the first signal x1, so it is you can see the amplitude is 1, and this is filtered output of first signal x1, so this will be y1. Now you can see the data here, and we can check the output. So the data is saying that it is a 0.8 volts. Similarly, it is though it is looking like a triangular wave, but it's not a triangular, it is a sine wave only, as we have reduced the number of cycles, and it's the interpolation of those points, and here in plotting the Matlab will join those points, so that's why it is looking like a triangular. Okay, and here you can see that amplitude of the second signal is also 1, but amplitude of second filter output is 0.5, and the first output signal amplitude is 0.8, and then the second output signal is 0.5, so you can easily understand that the 0.85 is greater. So to have a better understanding on this one, we have to write a digital frequency, so let's go with that one. So as I said that we have seen here, so we have to write cos omega by 2, and that absolute value we have to calculate, and if we draw the uh, graph for this one, we'll have one low pass filter output. Okay, so we'll write that also, and then we'll compare with our. So first defining omega, so omega select 0 1 to 0.0001 uh, 001, and then multiplied with pi, and then goes up to pi. Okay, so this is omega, so digital frequency, or you can say digital frequency. And next we have to define capital H. Capital H, we have seen that absolute value of cos omega by 2, right? And then defining a small frequency f is equals to in terms of digital frequency, so omega into fs right, by 2 pi, 2 into pi. Okay, now drawing the plot. So before plotting, we say figure 2. We'll try to separate the another plot for that one. So plot now f comma capital H, right? Now we run this. So once again, sampling frequency 4000, and then 500 and 1000. So this is our low frequency, low pass filter frequency model. Okay. Now we'll compare with the values. So we take the data point here and we place it here. So X, we'll drag it till 500. Okay. So this is 500. So here 500 is having a 0.9236. So here we'll take the data point and here we'll compare with that same thing. So it is nearly zero point 0.9. So as I earlier said that these values are reduced one, and interpolation values might be missed that zero point 0.9 value. So that's why it is displaying like this. So actually these are both are same. Okay, and here, and for 1000 frequency, this is 1000 frequency, and the data is 0.5. So here we'll go to 1000. So here you can see the 1000 is 0.707. Okay, so it is nearly the same. Once again, we might miss that point because of this less divisions in our output. Okay, and so this is the low pass filter. Similarly, we can make a small change in this program and make it as a high pass filter. Only difference will be after calculating this here, instead of this, if you take minus here, okay, and then do the calculation, here the cos will be replaced with sine omega by 2, and the same thing we have to do the changes here. So instead of half and half, we have to just write minus here, and then one more change we have to do is that this absolute value, instead of cos, we have to just write sine here. Now we can run the same program, and sampling frequency 4000 and 500, another is like 1000. Now you can see that this is high pass filter output. So here this is the high pass filter output. Now we can measure the outputs, as I said. You will get different values. Okay, hope you understand this. This is just simple filter. Okay, later in later sessions we'll try to do FIR low pass. We try to design FIR low pass filter. Okay, meet you in next video. Thank you.